Let's wait for a couple of minutes, then I will start. Okay, let me start. So this is the ninth week of the problem solving session of the Introduction to Atmospheric and Space Science. Today we are going to solve the week 9 assignments problems and some numericals based on that. And after that, particularly in the peak production, I would talk and how the production changes with height, and some further numericals will be there, and how hydrogen concentration varies in ionosphere, which is somewhat different than what we have studied, that any concentration of gases generally have an exponential decreasing tendency as it goes as we go higher up. Then the key concept of this the week 10 is Debye shielding. I will talk about that. Most of the thing I will focus on the derivation and the formulation, and after that the plasma frequency, and based on that some 3-4 numericals I have kept. This is the total thing today we will do. So I will start with the assignment. The first question in the assignment is which of the following EM radiation is or are responsible for ions production in the ionosphere? So in the ionosphere, we know that all the shortwave radiations which are present, they generally tend to make these ions. So X-rays is one of the shortwave electromagnetic radiation which creates ions in the ionosphere. Then extreme UV radiation is also there. Ultraviolet is also there, which also produces the ions in the ionosphere. Therefore, in totality, all of these will be the correct option for this particular thing. So I would write it here, just the shortwave radiations like X-rays, UV rays and extreme UV rays are responsible for ion production in ionosphere. The next question is, in the ionosphere, the order of peak electron density and the height from the Earth's surface where peak electron density is found are, so we know that the maximum electron density is found near the F1 to F2 transition layer. It's about 250 kilometers and its peak ionic concentration is 10 to the power 12 per meter cube. Therefore, that is the correct option. I have already discussed in the previous session and it is also there in the NPTEL lecture. Therefore, peak concentration is in the transition between F1 and F2 layer, that is at 250 kilometers from the surface, and concentration is of the order of 10 to the power 12 per meter cube. Okay. The next thing is that which of the following layers of the Earth's ionosphere disappears at night time? So here the correct option is D and F1. D and E is not the correct option. Of course, E also sometimes there is a tendency of disappearing, but mostly the D and F1 layers are there which disappears at the night time. Therefore, it's a fact-based question, so I would just write it here. The next thing is that which of the following is the fastest chemical reaction that occurs in the ionosphere? First is the radiative recombination, then dissociative recombination, then charge exchange, and all of these. The correct option is dissociative recombination. Why? Because the recombination rate of dissociative reaction let me write the actual value. It's about 10 to the power minus 13 per meter cube per second. Means per second it is creating about 10 to the power minus 13 per meter cube. So that is the recombination rate. For dissociative recombination. But for all other recombinations, it is of the order of say 10 to the power minus 18, which is less. Therefore, that is the fastest. Fine. Now this is a numerical question. Sixth is also a numerical question. I will come to it. I have put it in the other slides. Come to eighth question. The reaction X plus H nu gives X plus electron is known as. Now, as we can see from the reaction only, we can intuitively say that since a particular atom or molecule, whatever is given in this question, is reacted with photon. Since it is reacting with photon and hence it is giving ions and electrons, therefore this process is the photoionization. Because H nu is the photon which is reacting with the atom or the molecules to form ions. Therefore, this correct option is photoionization. So for 8, photoionization is the correct option. And its reaction is of the order that X plus H nu will give some ions and electrons. This is the photons. The term kT by mg has the dimension of energy, length, temperature, and none of the above. See, this kT by mg, if you see it properly, this kT by mg is actually nothing but the scale height, which we generally write it as RT by G. Okay, so this R is the specific gas constant, remember, specific gas constant. How can we write this? Because this Boltzmann constant is nothing but Avogadro number into R star. Okay, sorry, R star by Na. So this and this mass is there, which gives the molar mass into T by G, and that is giving this. Therefore, since it is a scale height, it should be meter. Or you can just break up this particular, that Boltzmann constant has energy of joules per Kelvin into Kelvin. Then you have to give the mass. And in this way, if you continue to do it, meter per second square, it ultimately will come to be meter. You can check it also. If it is Kelvin, Kelvin cancels out. Joules is kg, meter per second square, into meter, because it is work done unit. So it's force into distance divided by meter, and this is second square, which is present here. So second square, meter, meter cancels. This is kg is there. So kg also cancels. Remaining is meter. So meter is the, or length dimension is the correct option. Fine. Okay. Now the 10th question is, which of the following is or are the assumptions of the Chapman's theory of layer production? Well, the assumptions I have already written in the previous session. Also you can find in the NPTEL slides. So all of the above is the correct option. The atmosphere is isothermal, so that scale height remains similar and it is horizontally stratified. Second option is the incident radiation is monochromatic, which is very odd, but we have taken this particular assumption, and the atmosphere is made up of only one gas constituent. This is what These are all the Chapman's assumptions before deriving that peak production thing. So this is the last question here. Other three numerical questions I will solve. This is the ninth question. Fine, this is done. Yes. So this is another assignment question. It is given here, if the recombination rate of the reaction is 10 to the power minus 8 centimeter cube per second, then calculate the value of the time constant if the electron density is 10 to the power 12 per meter cube. Before that, I want to I have written a wrong unit here. This should not be this. This is meter cube per second, as you can see here. Okay. Fine. Therefore, given here, the recombination rate, we call it alpha. This is 10 to the power minus 8 centimeter cube per second. Now, if I have to convert it into meter, then what will happen? See, 1 centimeter, simple conversion, is 10 to the power minus 2 meter. Therefore, 1 centimeter cube will be 10 to the power minus 6 meter cube. Right? Now, just you multiply by 10 to the power minus 6. So, it's 10 to the power minus 8 into 10 to the power minus 6 meter cube per second. That gives 10 to the power minus 14 meter cube per second. Fine. Now, calculate the value of the time constant if the electron density is this. Now, given another thing, that is the electron density, Ne, that is 10 to the power 12 per meter cube. Okay, this is the electron density. Now, you have to calculate the time constant. Now, what is the formula of the time constant? So, formula we will apply. Time constant of all these reactions which generally takes place in the ionosphere is given by tau is equal to alpha, the recombination rate, times the number density to the power minus 1, or it is 1 by alpha into N. Therefore, this time constant tau will be 10 to the power minus 14 into 10 to the power 12 to the power minus 1. Just a minute. Yes. So tau will be equal to 10 to the power minus 2 minus 1. That becomes 10 square seconds, or that is equal to 100 seconds. So if you come to that particular question, it's 100 seconds is the answer. So this is the answer. This is the time constant. Okay. Now going to the next question. It is given here, if the electron density of an ionospheric layer is this 8.1 into 10 to the power 11 per meter cube, then the maximum frequency of the radio wave which can be reflected back from this layer on the vertical incidence will be. So it is, you can see that the radio waves, frequency of the radio wave which can be reflected back, which is nothing but the critical frequency. And critical frequency is nothing but that plasma frequency, which we will discuss today. But this critical frequency is given by Fc, root over 81 into Ne. But Ne should be in per meter cube. Okay. And it is given in per meter cube, so we don't need to change the centimeter cube to meter cube again. Therefore, given here, let us write that Ne is 8.1 into 10 to the power 11 per meter cube. So this critical frequency is just one line formula. It is 81 into 8.1 into 10 to the power 11. Simple. So FC, just write 81 here and make this 81, then it will be 10 to the power 10, one less. Then FC, see 281s are there, we can take 181 out, and root over 10 to the power 10 is what? 10 to the power 5, because it is in the powers. Therefore 81 into 10 to the power 5. Then what will happen? I will take 8.1 into 10 to the power 6, and the unit of frequency is per second or hertz. Therefore it will be 8.1 megahertz. Okay. Now we can check the answer here. Yes, it is 8.1 megahertz. And the seventh question is a very known question. We have done it multiple times in the previous assignment questions, as well as we have solved. And today also I have given 2 questions based on this. So this is the question. This is the first question. So we will do this after this. Yeah. The height from the Earth's surface at which the air density becomes 1 by 100 times the density of the Earth's surface is. Assume the scale height to be 7.5 kilometer. See here, temperature variation with height is not given. So I will take as it is an isothermal atmosphere. It is an isothermal atmosphere. Then only this is true, that scale height is 7.5 kilometer throughout the atmosphere. Okay. So now density variation takes place exponentially with height, just like pressure. Therefore P, we write it as P naught e to the power minus z by h. Similarly we can write now, since it is an isothermal atmosphere, what is there is that if we write the ideal gas equation, then it will be rho r into T. This is the ideal gas equation. Now if it is an ideal gas equation, this is constant, R is specific gas constant, therefore P and rho are proportional. Therefore P is proportional to rho, and this expression therefore in pressure can be written as therefore rho is equal to rho naught e to the power minus z by h. Now we use this this question, whatever given, that density at what height becomes rho naught by 100. Density of the Earth's surface is rho naught. This is the density of the Earth's surface. It's a good revision that this question repeats again. So this is rho naught by 100. This is given. This is given, right? Therefore, we can write rho is equal to rho naught e to the power minus z by h. Therefore, this is rho naught by 100 is equal rho naught e to the power minus z by h. Rho naught cancels. Take log. This is 1 by 100. This is minus z by h. So if I just change it to log 100, this minus goes. Z will be h log 100. Z will be h log 100. Now, so I need to find out z. Let me do it somewhere here. Therefore, z will be equal to, given it is 7.5 kilometers, let me write it like that, log of 100. Okay. So now, if we calculate it out, let me calculate. Log 100 is about 4.9 605 and this is 7.5 into 7.5 if you do, it comes out to be about 34.53 kilometers. So this is the height. Okay, let us check it. This is the last question. Yeah, it is 34.5 kilometers. Okay, so all the questions of the assignments are now solved. Now we will go to the week 10 things, so that I have chosen those particular areas from where I have seen the questions in the assignment 10, and left I think only one topic where the collapsing of the layers are taking place, so I will not do that. It is well mentioned there. Okay. Now peak production, we have stopped it here in the previous session. So the formula for the peak production the formula for the peak production was Q, which is a function of chi and h, will be Qm of where chi is equal to 0 and h is equal to the peak production height exponential. We have written 1 minus zeta minus sec of zeta e to the power, sec of chi, the zenith angle, minus e to the power chi minus zeta. So this is the exponential expression which we have found out for the peak production. Okay, this chi is, just reminding, this is the zenith angle, that is, this is the earth, this is the normal, and if the radiation comes at a particular angle, then it is chi. Okay, now this is for the 0, that is for the normal incidence, and e to the power these things. Now what is z here? Z or zeta, whatever you say. Zeta is, it is defined above the peak production, height above the peak production. Okay. How it is defined? Now zeta is, we have seen it, h minus hm divided by capital H. What is this capital H? Scale height. Now what is this hm? Sorry, hm is your peak production height, the height at which the peak production takes place, and h is any arbitrary height, so it is, this z is representing that it is some height which is above the peak production. And also we have got another expression that E upon hm by capital H is actually a rho naught into h. Actually this is hm0. Why hm0? For chi is equal to 0. Because actual expression is e to the power hm by capital H is equal to a rho naught h sec chi, where sec chi is your zenith angle related term, h is the scale height, rho naught is the density, and a is the area of cross section. Okay. Now here if we apply the continuity equation in this ionosphere region, the continuity equation looks like something like this: d dt, the total derivative of the electron concentration which is produced, will be production minus loss. Ultimately this should be the thing, and there will be plus minus some transport if you want to add. Okay, now if we are considering the steady state in the atmosphere, now these electrons are not a, electron concentration is not a function of space. It's not a function of space. If not a function of space, then for steady state this d e dt will be equal to 0. There is the equilibrium state, that is production will be balanced by the loss. Simple. Transport is negligible, let us consider. Therefore, we can write Q will be equal to L. And what is L? L is also defined as alpha into electron concentration square. Right? Now, what is alpha? Alpha is the recombination coefficient. Recombination rate, which we say. Recombination coefficient. This we have seen in the earlier sessions also. We have seen. So this electron concentration will be therefore Q by alpha root. This is the expression which we are getting. Now, if we have to write the Q, this expression over here, then what we can write? We can write that electron concentration will be equal to root over Qm0. Qm0 I am writing because for the zero zenith angle. Okay, so this thing you can write it as Qm0. So Qm0, 0 hm also you can see, divided by alpha. But this term is there, exponential term is there, and there is a root also present. Therefore, I will write it as exponential half of same thing 1 minus zeta minus sec chi e to the power minus zeta. So, this is the electron concentration, and this electron concentration is nothing we can write as any, the density of the electrons produced. Okay, and this thing I will write this thing I will write as Ne will be equal to Nem, because if you see this Qm0 upon alpha, that is the number density of the electrons produced at normal incidence. Chi is 0. Chi is 0 means normal incidence. So if there is a normal incidence, how many electrons per unit volume is produced is this. Okay, because we have seen that the concentration of electrons is given by Q by alpha. Okay. Therefore, Nem exponential, same thing which I will write of 1 minus zeta minus sec chi e to the power minus zeta. That's all. And you can write this Nem will be equal to root over Qm0 of 0 zenith angle, because it is of the normal incidence, divided by alpha, the recombination coefficient. And therefore this Ne, which is Q by alpha, is the Chapman alpha layer, we say. Means in the Chapman alpha layer, this is the number of electrons per unit volume produced. Fine. And also from this this equation, we can write that if we take the ratio of this, then we get if you take the ratio of this, so Q divided by Qm0 is just exponential of 1 minus zeta minus sec chi e to the power minus zeta. That's all. These are the things which we can derive from the peak production equation which we have got. Now, several facts related to the peak production equation. There will be total 6 facts which is there. The first thing is that peak production happens, there is a condition, peak production happens when the number density of the ions or the electrons times the sigma, that is the area of cross section, this should be equal to 1. This is a condition, or Nm should be equal to sigma inverse. This is one of the conditions. The second condition is, which we have seen, that the rate of production is simple. This we have derived. This is very important. The rate of production is given by QE is equal to QM0 exponential of 1 minus zeta minus sec chi e to the power minus zeta. Simple. This is we have seen already. Okay. I go to the third thing, which is very important, that this peak magnitude QM, third thing, is the peak magnitude, peak production rate, I would say. Okay. This Q is the production rate and QM is the peak production rate, which is given by, not for normal incidence, this is for the general incidence. This is for the general incidence. This is eta I infinity divided by E into H. This E is not electron or charge of the electron. This is exponential 1. This is e to the power 1. Okay, and this is cos of chi. So we can see that it is related to chi. Now for QM0, for normal incidence, this becomes QM0, that is eta I infinity divided by EH. So what we can see, this peak production, the peak production rate does not depend on area of cross section. Right? It depends on the number density, it depends on the initial radiation which is coming, it depends on the scale height and the zenith angle. And for normal incidence, of course, the zenith angle is your 0. So cos 0 is 1. Right? Okay. The fourth important fact, which is a very important figure as well, that is, if we draw this particular figure corresponding to this particular formula, this one, oh sorry, not this one, sorry, this one, then we get, suppose this is the height HM, I would say. Okay. Now what happens is that this is the curve or corresponding to that formula which I have just ticked, and this is how it looks. Okay. It's becoming more like this and ultimately this. Fine. So you can see that this H minus HM divided by capital H, you can say that this is H. Now this is for chi is equal to 0, this is chi for 45, this is chi for 60, and this is chi for 75. Now see, as in chi is equal to 0, the height of peak production is minimum. Minimum means at low altitude we get peak production. Right? And as chi increases, as chi goes up, we can see that this HM also goes up. Okay. Another thing, for chi is equal to 0, okay, sorry, this is the Q by Q naught. You should remember this. Okay. Q naught or means QM. Okay. Now, wait, let me add one slide here. Let me draw it here. This will be good to demonstrate. It is important. So now I am drawing this. Right? This is H. This is Q by QL. Now we'll change the color here. So this becomes chi is equal to 0. This is chi is equal to 45, this is chi is equal to 60, and this is chi is equal to 70. Okay, now what we can see is this height of peak production is decreasing. So this for chi is equal to 0. Another thing is that the production is maximum at any level. So as chi increases, production is minimum. Why? Because more will be the loss, attenuation loss. As chi increases, so what is happening is that it has to travel lots of region of the atmosphere because it's a slanting ray. So it will attenuate its energy. So if it attenuates, less will be the production. So this is what is happening here. Okay. And another thing which I have already showed, that for chi is equal to 0, the peak production height is lower. As the chi increases, the peak production height also goes up. Okay. Another is the fifth one. The fifth one is the height of the peak production. Let me write. Oh. The height of the peak production is Hm is equal capital H log of sigma capital H n naught sec chi. What you can see is that this is the area of cross section, which generally we have written in the earlier session as A is the same thing. H is the scale height, n naught is the number density eta, and sec chi is, you know that it is the, in fact this n naught is nothing but rho naught, because rho naught will be proportional to n naught, the number density. Okay, so this is the formulation, and what we can notice here is that this Hm is not dependent on the radiation, the incident radiation. This is an important observation. Fine. Okay, and next is that Q0 which I have mentioned, that I have already told. So there is nothing much left. Okay, so these are the 5 main points related to the production rate, related to this particular formula. Right? So I will now go to the production with height. This is just a minute. Yeah, the production with height. See, any gas constituent in the atmosphere, what we know from our earlier knowledge, what we have seen in this particular course, is that you go with pressure, you go with temperature, sorry, not temperature, density, you go with the number density of the gases. What we have seen always is that with height, pressure you can say, or rho and n, whatever, it is always exponentially decaying. It is always exponentially decaying function, because P is equal to P naught e to the power minus z by h. Similarly, rho will be equal to rho naught e to the power minus z by h, and n is equal to rho naught, n naught e to the power minus z by h. So surface to the top of the atmosphere, as we go higher and higher up, of course, there is an assumption that it will be an isothermal atmosphere. Then only this formula is valid. Otherwise also there will be decrement is there, but with a power based on the lapse rate, which we have seen. But hydrogen, particularly in the ionosphere, behave something different. So I will write certain some equilibrium concepts and prove that it decreases means this hydrogen ion concentration, instead of decreasing with height in the ionosphere, it increases with height only in the ionosphere, remember. So hydrogen in ionosphere. Hydrogen in the ionosphere. Okay. Now, solar radiation, as I was discussing the first question of this week 9 assignment, where the shortwave radiations all are detailed there in the options. So it consists of X-rays, EUV rays, that is the extreme UV rays, and UV rays are also there. So these solar radiations or shortwave radiations, this creates the ions. Okay. Now hydrogen is also light in density. So it is light. So it is generally found in the upper atmosphere, particularly in the ionosphere region. Not much found in the troposphere, but mostly in the upper atmosphere it is found. Why? Because its density is low. Fine. Now a chemical reaction I will write, which is a kind of a photoionization kind of. So H plus H nu, the photons, but it should be less than 90 nanometer. It should be less than 90 nanometer, and that becomes H plus electron. Right? Now what hydrogen does is that, this hydrogen ion does is that, it exchanges the charge with oxygen. So this is a nascent oxygen, it becomes O plus plus H. So it's charge exchange mechanism. So let me write it, is charge exchange. And because of this only, the anomalous thing happens. So how it is happening? So equilibrium, concepts of equilibrium, if you remember, it is generally concentration of hydrogen will be just this forward thing, these things. So H plus into O. Fine, this is proportional to this, and H plus, the ions, will be proportional to hydrogen divided by oxygen. This is the concept of the equilibrium, so you can. And now this H plus, concentration of the hydrogen ions, will be proportional to exponential of, now if we write using this particular formulation, we go by minus H, instead of Z I am writing H of capital H of H, plus, because it is in the denominator, so it will go in the upper numerator, so it will run plus by H of oxygen. Now if we know that this scale height H0 divided by HH is actually 1 by 16. See, 16 times the H0 is actually HH, because it is inversely proportional to M. See, this is R star by M T by G, right? That is your scale height. So it's inversely proportional to the molecular mass. So that's why we are writing like this. Okay, so HH will be 16 times H of oxygen. Now if you put it here in this expression, then what will happen? See, this H plus is proportional to, therefore, exponential of minus H by 16HO plus H by H. Just replacing this HH. Therefore, H plus will be proportional to exponential of 15H divided by 16H0. Right? Although this is small, but exponential is having a positive sign. Therefore, there is an increment, you can see, but within the ionosphere layer, remember, there is an increment. Fine. So this is different than that what we have seen for the entire atmosphere, where any gas constituent generally decreases with height, but hydrogen ions in the ionosphere, due to this charge exchange process, have a peculiar behavior that hydrogen ions is exponentially growing in the ionosphere, not decaying. So this is a different thing. This is an odd thing which happens in the ionosphere. The immediate next concept which is covered in the NPTEL this Week 10 courses is the ion atom rearrangement. So in that, generally to understand how this F1 layer, these things collapses, peak collapses, since I have not seen too many questions based on that, so I am skipping that particular topic. You can understand easily from that NPTEL slides. But let me do some numericals which will be helpful for solving the assignments. And also I will take Debye shielding theory and Debye potential. Corresponding to that also the Debye length and plasma frequency, the Debye parameter, all these will have some numericals in the assignment 10. So I will cover also those numericals. Fine. This is another question which is based on that the previous concepts which we have studied. So what is the scale height of the atmosphere if it consists of oxygen atom and the temperature is 27 degrees Celsius? It's simple question, nothing to worry about this. So it's nothing but n is equal to n naught e to the power minus z by h, because here it is mentioned that temperature is 27 degrees Celsius. So it is throughout the atmosphere. We will assume again isothermal atmosphere. So what will be the temperature? It's not 27 degrees Celsius. Remember, it has to be converted into Kelvin. So 27 degrees Celsius plus 273. So it will come out to be 300 Kelvin. Okay. Now, what about? Okay. Oh no, just it is the scale height. The scale height which you need to be found out. Okay. So what is the scale height expression? Scale height expression is R T by G. This is the expression. Now this R is the specific gas constant. You have to remember this thing. This is the specific gas constant. Right? So it will vary. If the gas constituents varies, then this R will also vary. Now how will I calculate this R therefore? I know that R is nothing but the universal gas constant divided by the molar mass or the atomic mass, whatever you see. But here we have said that atmosphere is only consists of oxygen atom. So oxygen atom, its corresponding molar mass is what? 16, right? 16 grams per mole for oxygen atom. Now had it been oxygen molecule, it will be 32 grams per mole. Remember those things. Okay. So R will be, now this R star is known expression, it's 8.314 joules per Kelvin per mole, and M is 16 grams per mole. Remember, this is grams. We have to convert it into kg. Therefore, we have to multiply by 1000. So 8314 divided by 16 will be my answer. So we will see. It comes out to be about 519.62 joules per Kelvin per kg. Now just to recap it, for the dry air it comes out to be about 287 joules per Kelvin per kg. For the vapors it comes out to be about 461.5 joules per Kelvin per kg. Just for recapping case, I am just writing, but you can see that if there is an oxygen atom throughout the atmosphere present, then this will be the value of the specific gas constant. And if we know this R now, we can easily find out H. How now this G is 9.81 meter per second square. So H will be equal to 519.62 into 300 divided by 9.81. So if I calculate, it's 519.62 into 300 divided by 9.81. Well, so it comes out to be about 15,890.5 meters. So it comes out to be about 15.8 kilometers or roughly 16 kilometers. That's all. So this is just a question related to scale height. Just only thing we need to know here is that what is the atomic mass of that particular constituent if it is throughout the atmosphere. If more than one thing is given, suppose hydrogen and oxygen both are given, then you have to calculate the combined masses, that is m bar. So m bar will be that m1 into percentage contribution plus m2 into percentage contribution of the second divided by 100%. This is how we have to calculate. We have seen, we have already done this earlier. Okay, now this concept is done. Hydrogen in the ionosphere also I have done. So I have to skip this slide. Or if I yes, so hydrogen in the ionosphere, it behaves something different. So all other gases goes like this. So this is your n, this is your height. So with height, all gases decreases. What I mean by all gases is that all gases concentration decreases, but in the ionosphere zone, only in the ionosphere, remember, in the ionosphere, this H plus concentration, if we draw with height, it increases. Okay, so now this is only in the ionosphere, which I have already written, but what is the reason? Due to the charge exchange. That's all. Now we will go to the device shielding process. Just a minute. Okay, this is now the Debye shielding process, where we talk about the Debye length and the Debye potential and the plasma frequency, which is mostly related to those things, and ultimately at the last some numericals which I have put, which will be helpful for solving the assignment problems. Okay, so Debye shielding process is particularly in plasma, only for plasma. Now, what is a plasma? Which has high concentration, or you would say high density, high concentration or high density high density of ions Now, so suppose you have a plasma and which has all the positive and negative charges. So all the positive and negative charges are there. And you apply some electric field in this direction. Some electric field is applied. Just a minute. Yeah. Okay. So now the electric field is applied in this plasma. So we have to remember that before applying this electric field in the plasma region, the amount of positive charges, or I would say the charge density defined by this rho, so it is charge density, let me write it. What is this charge density? It is the charge per unit volume. See, charge density sometimes can be written as charge per unit area also, charge per unit volume also. But here we are considering charge per unit volume. You can consider charge per unit area as well. So it's not a big deal. So here in a plasma, without this electric field, this rho of plus, all the positive charges or the volume density should be always equal to this rho of minus. It is always. And the number of ions will be equal to number of electrons. Okay. Now if we apply some electric field, how we can apply some electric field? Now you externally put a positive test charge. We know that in physics we have seen, so if we put a positive test charge and there is a unit charge which is present, so this, how much influence of this positive charge is taken up by this, the unit charge is nothing but the electric field. And this electric field, we have written always kq by r square if this charge is q. Okay, so this is how we write the electric field for the Coulombic force of attraction. Now what will happen is that within this plasma, if we put a positive test charge, then what will happen? Intention means intuitively what should happen. See, these electrons are present, positive charges are also present. So electrons will start attracting towards this particular positive charges. Okay, but these positive ions will be remaining there, whose motion will be less as compared to that of the electrons. Why the motion of the positive ions? So let us write a question here. Why motion of ions will be less, than that of electrons. This is because what is the mass of electron and what is the mass of the ions? See, mass of electron is always less than mass of the ions because this is the minimum. Not minimum, but as compared to the ions, it is less. 10 to the power minus 31 kgs. Okay. So this Me is always less than Mi. And according to the VRMS, that kinetic theory of gases, if you remember, this VRMS is nothing but 3 kBT by M. So it is inversely proportional to the mass. Therefore, velocity of the electrons will be much greater than the velocity of ions. So this is the thermal motion. Because of this temperature, the motion of the electrons. Okay, so there will be thermal motions of the electrons. Now this thermal motion will not properly form this electron cloud across these positive charges. Now had the thermal motions less, more beautifully the electron clouds can be seen. Where? Surrounding the test charge, which is introduced. Okay, so this is the thing. So ions in the backgrounds are more or less stationary, whose charge densities are fixed. But since we have given a positive test charge, electrons forms clouds over here, over these regions. Coulombic attraction is also there, but because of the thermal motions, the entire attraction or neutralizing process will not take place. Okay, and because the electrons are forming clouds here, electron concentration per unit volume over here and electron concentration per unit volume over here will be different. That is the key point here. Okay, fine. The next thing is okay, I have talked about the random thermal motions also that will not allow these electron clouds to form properly, or the Coulombic attraction which is there, which has an opposing effect of these thermal motions. Okay, now certain things we will understand, particularly based on the potential. So here, if you take a plasma in general, which I have already told just now, that if this is a plasma, suppose, ideally it is neutral. Ideally it is neutral. But if we introduce some positive charges over here, this neutrality goes. Right? Now, the first point is that the number of electron per unit volume into minus q, suppose I am writing for the negative charges, will be always equal to Ni into plus q when it is for ideal plasma, when no test charges are put. Okay. Now its corresponding potential, if test charge, which is of which sign? Positive charge. Okay, test positive charge is put, which is creating a disturbance in the plasma. What will happen? At t is equal to 0, immediately as I put a positive test charge, the potential, electrostatic potential or Coulombic potential, will be nothing but 1 by 4 pi epsilon naught. Q is, suppose, this particular thing, divided by R. And what will happen? The situation will happen what? So as t progresses, this is the t is equal to 0 situation. As t progresses, at t is equal to t, this is the positive test charge, and all electrons will form a cloud over this, and positive ions will remain as it is wherever they are, not much affected by this positive charge. Of course, there will be slight affection, some repulsion will be there, but mostly remains stationary. Okay, so I will write it here. This we can neglect. Motion of ions and treat them as background. Okay, and if you say in more better way, then I would say that the number density of ions, or the charge density of the ions, will be some constant value n naught. It is fixed, it is not changing much. Okay, but not in the case of electrons. Very initially, when there was nothing, it was Ne is also equal to n naught. But as I have introduced some positive test charge here, electrons are now changing. This means the concentration of the electrons will be changing. So how it will change, we will see that. Okay, and well, near the positive test charge, what is happening? This Ne is much greater than Na, but as you go far away, this Ne decreases. Right? This is also very clear picture from this particular thing when we have introduced the test charge. Already I have mentioned that charge density is defined as charge per unit volume. This I have already defined. Now this positive test charge which we have kept to disturb this plasma, now up to what distance this positive test charge influence can be felt is given by lambda d, and this lambda d is d by length. Now in electrostatics, what we have done, there is a positive charge and its influence can be felt up to infinite length, right? But in the plasma, in case of plasma, the distance up to which its positive charge's influence can be felt is the d by length given by lambda d, and we will derive what will be the expression of this lambda d, what will be the expression of the potential. Say suppose we have seen that at t is equal to 0, the potential is a simple Coulombic potential. But what happens at t is equal to t? What is the potential over this region? We don't know. This we need to find out. Okay, this is another concept. Now this d by length and potential thing will come with a derivation. So I will just first note down what will be the objective of our derivation, some facts related to the kinetic theory of gases, and then we will derive the expressions. So this is the main thing. So the objective, here is number one, to find. So we have seen that the potential at t is equal to 0 is just the Coulombic potential. So to find the potential, after sufficiently long time, okay, and what will be the potential, the second thing, what will be the potential at distance less than lambda d and greater than lambda d. Third, expression of lambda d, how we can calculate this lambda d, that is how we can calculate 1 d by length. Okay, so these are the certain objectives which we will do. So in E and in I are charge concentration, nothing but the charges per unit volume. What we have called earlier that Ne as the charge density, same thing. This is the charge concentration per unit volume. Okay, and of course near this particular test charge this Ne number will be much greater than Ni, which we have seen. Okay, therefore in that vicinity the effective charge is given as Ne minus Ni. Why? Because the charge concentration of the electrons is much greater than charge concentration of the ions. But ideally what happens, which I have repeated so many times, that Ne should be equal to Ni in plasma. It happens. Okay, that creates that net charge density is equal to 0. Therefore, based on this effective charge concept, this rho is Q times Ne minus Ni. See, this is the number per unit volume. Okay, this is number per unit volume, or you can say the number density. So number per unit volume. But if you multiply it with charge, this becomes charge per unit volume. So actually this is the charge density. When we are talking about the concentrations, this is number per unit volume. When we are talking about the charge, this is charge per unit volume multiplied by Q. Okay. Also, we know that from Gauss law of electrostatics that del dot E, the electric field, is nothing but rho by epsilon naught, where rho is the charge density and what is E, the electric field. This we know. And we also know that this E is a conservative kind of a force. Of course, this electric field is a force. So this is a conservative force. So what we can write is that this electric field can be written as minus gradient of some potential phi. Correct? Now just put it in, put it in this expression del dot E is equal to rho by epsilon. So if you put this in this, so it will be del dot minus grad phi, that is equal to rho by epsilon naught. What we get, so it is dot. Okay, so it is minus grad square phi is rho by epsilon naught, or grad square phi is minus rho by epsilon naught. Fine, this is the expression which we have found out, which is a Poisson equation. These are Poisson's equations. Now had it been 0, this is the normal Laplace equation, which we expect in the plasma, ideal plasma situation. But now we have put an electric, some electric field by introducing a test charge. Therefore, some charge density is appearing, and hence we are getting a Poisson's equation. Okay. Now, del square phi, or the Laplacian of phi, will be just take the expression of rho from the previously which we have seen, which is Q into the Ne minus Ni, the effective charge concentration, divided by epsilon naught. Right? Now Q is, let's say, for the electrons, so it is minus E. This is Ne minus Ni divided by epsilon naught. Fine. Now assuming thermodynamic equilibrium, and using Maxwell-Boltzmann statistics, these are all kinetic theory of gases expressions which I am using, is Boltzmann theory. We actually can write N is equal to N naught exponential of minus E by kBT. Fine. This is the concentration. This is also the concentration at the 0th time, or fine, or electron distribution function will be something like this. F of n is A exponential of, see, energy, this is the total energy, kinetic plus potential. So how we can write kinetic energy? This is minus sign is already there, okay? So F m into u square, some velocity, okay, and E into phi. Now how we are writing E into phi? We are writing E into phi because, see, do one thing, take this bracket off or I erase it. Just a minute. Okay. Yeah. Just a minute. Yeah. So this is the thing. See, I have written plus E phi. See, if we have a potential whose expression is what? Kq by r, and we know that energy is kq by r into q. Therefore, q into v is actually E. Means E, this is the potential energy. This is the EP, potential energy, right? Now, q here is minus E. So, minus E into phi is nothing but the energy potential. And there is a minus sign, so minus minus becoming plus. Simple. This is the expression which we are getting. Now, we will say that, just a minute. Yeah. This ions, Ni is always equal to N naught. What about N electrons? These N electrons will be the original number of things when no charges were introduced, which is nothing but N naught. When there was nothing in the plasma, we have not introduced any electric field in that plasma, nothing has happened, so Ne will be also N naught, same amount which we have seen. But as I introduced an electric field, Me will be now becomes N naught exponential of minus E phi by kBt. I am not considering the kinetic energy part, only the potential energy part we are taking in. So we are assuming that no motions are taking place, only it is over the plus charge, it is the electron concentration which is coming. So no thermal motions, so no motions of ions or electrons. Okay, is an assumption, you can say assume. Fine. So this is what we are getting. Okay. Now, how we can write? Say we have already seen that it is not minus; they should be always plus. Okay. Fine. Now, I get back to this this expression and write, so grad square phi is nothing but minus E by epsilon naught, and there is Ne minus Ni. See, already I have seen that this is, there is a minus E which is there. Okay, so now what I will do is that I will write in I yes, oh just a minute, something is, see, this is minus rho by epsilon naught, right? So this will be minus q as per the previous expression, this one. So rho is equal to q Ne minus Ni. If you just put it here, it will be a minus sign, right? Now if we put q is equal to minus E, this is plus, right? Okay. So now this, I have taken a minus sign, it was plus, I have taken a minus sign, so it will be Ni minus Ne. Therefore, minus E by epsilon naught, Ni is N naught minus N naught exponential E phi by kBt. Remember one thing which I suddenly got, this kBt is generally given in electron volt. So 1 electron volt is actually 1.6 into 10 to the power minus 19 joules. 1.6 into 10 to the power minus 19 joules is 1 electron volt. It may be required sometimes for numerical solving. Okay, so this is what it is. Coming back here, and let me take out the N naught, and we get 1 minus exponential E phi by kBt, right? Now, in the next step, if we assume E phi, the potential energy, is much less than kBt, it is very small, then we can write this grad square phi will be equal to minus E n naught by epsilon naught 1 minus, what we can write the exponential, just 1 plus E phi by kBt. Why? Because e to the power x is nothing but, means for small order approximation it's 1 plus x. Other terms we are neglecting or truncating. Okay, so now next, also this is the plasma frequency again. Just a minute. So I will just erase this portion because we know this particular thing. Okay, now this becomes grad square phi will be minus E n naught divided by epsilon naught. It is 1 minus 1 which is crossing, and there will be minus E phi by kBt. So this minus chops out. So what you get, E square n naught phi divided by epsilon naught kBt. Right? Now this thing can be further written as grad square phi is equal phi by lambda d. Lambda d square. Sorry. Fine. And this lambda d is therefore written as epsilon naught kBt divided by E square n naught. N naught is the total number density of the what you call as your plasma. When a test charge is there also, still it is the N naught net, and epsilon naught is the permittivity of free space, Kb is the Boltzmann constant, T is the temperature of the plasma, E square is the charge, electron charge, which is of same unit but in coulombs. Okay, so this is the d by length. This is the d by length. Now, so I am continuing in the plasma frequency also, but some things are left. So now this grad square phi, I will write it as 1 by r square delta delta r square delta phi by delta r only. So we are not considering theta and phi directions. Okay, so this grad square phi, so it will be, the main equation will be ddr, because other things I am not considering here. So it's d phi dr, it's only a radial potential, and that is equal to 1 by lambda d square phi of r. And generally the solution of this becomes phi of r will be equal to 1 by 4 pi epsilon naught q by r e to the power minus r by lambda d. This is the potential solution. Okay, So this is the potential. So we can see there is the Coulombic part. This is the Coulombic potential, well known, and this is the exponential part. Right? Now, how will it look like? It will look like this. So this is the, so Coulombic part is normally is this, the rectangular hyperbola kind of. This is the potential, this is R, right? But here it will be like this. So it falls, then again like this. This will be the phi. This is the Coulombic. So after d by length, lambda d, it falls like this, exponential. Right? This is how it happens. And so we can also calculate phi of lambda d. What it will be? It will be 1 by 4 pi epsilon naught q by lambda d e to the power minus 1. So earlier at r is equal to some lambda t distance, if it's a Coulombic potential at t is equal to 0, it is only the Coulombic, this one. But now it is 1 by 4 pi epsilon naught lambda d e to the power 1 on q over q. This is the potential at lambda d distance. Okay, and at 2 lambda d distance, so it will be phi of 2 lambda d, that is equal to q by 4 pi epsilon naught 2 lambda d by e square. Fine. So this is the frequency. Is not frequency. This is the potential which we have derived. So this is the potential. So we have derived here the potential, the equation, and we have also derived the d by length. Next is the plasma frequency, where I will just give a quick idea and give a small derivation of this particular thing, and then we'll solve 3-4 numericals, which is easy, and we can wrap up after that. So plasma frequency is the next topic. See, this frequency arises because some kind of oscillation will be there. What happens is that if an electron is present and you are given some electric field, so somewhere, so from here some electric field is given, so electron moves in the direction of the electric field, but there will be some random thermal motion also of the electrons. So thermal motions are also there. With the same logic that the mass of the electron is much less than the mass of the ions, so V of electron is much greater than V of I. So this is based on the thermal motions. Why? Because it is coming from 3 kb T by m. So T is also there. 3 kb T by m. So T is also there. So thermal motions are also there. So these thermal motions generally provide a restoring effect. And hence there is an oscillation kind of thing. Okay, this is the plasma oscillation also, you can see. Okay, so these electrons should move towards the positive test charge if it is introduced here in the opposite direction of the electric field, because the electrons moves in that way, but due to the thermal motions it may move like this. So there is an oscillation which is present. So that oscillation's frequency is plasma frequency. Simple. This is the concept. Now, for deriving this, they have separated the electrons into these two plates will be there, like a plate of a capacitor. The electric field is, so it is written in this way. See, by some mechanisms, we displace all electrons by some delta x distance. Okay, and all electrons are here and all ions are here, like that way. So it's a kind of a capacitor ring. So the charge density for a plate is Q by A, the charge per unit area, and the electric field, we know that in case of capacitor is like this, sigma by epsilon naught, isn't it? So means for a plate, charged plate having charge density sigma, the electric field is given by sigma by epsilon naught. Now how we can write this? This is minus E into N naught into delta x. What is N naught? N naught is the number density of electrons, right? So this is the charge, this is the number density of the electrons, and this is the delta x. Now check the unit. This is charge per unit area only. Why? This is the charge per unit volume was there. This is the length. So length and volume is in the denominator. So it cancels out and we get this. Okay. So we get minus E N naught delta x divided by epsilon naught. Simple. Okay. Now equation becomes mass into acceleration becomes minus E into E, and that provides. Okay, so now another thing is there. Let us consider it for the ions. So number density of the ions, let's say. Okay, so this will be plus to understand the things. Or what you can do is that this is minus, it's fine, this is for the electrons, and there will be, this will be minus of minus sigma. So it's minus sigma by epsilon naught because it is from the negative plate, right? So this becomes E N naught delta x by epsilon naught. So E minus E into E, so it becomes minus E square N naught delta x by epsilon naught. Right, now just solve the equation, and the frequency is this particular term. So it becomes omega plasma is root over E square. So this is nothing but minus omega square delta x E square N naught divided by epsilon naught m E. This is all for the electrons. Okay. So now, just a minute. If I see this E is known, epsilon naught value is known, so let's write it. E is 1.6 into 10 to the power minus 19 coulomb. ME is 9.11 into 10 to the power minus 31 kgs, and epsilon naught is 8.85 into 10 to the power minus 12, right? And this will be, what is the unit? Newton meter square per coulomb square, right? You just put on those values, and ultimately what we get is that 9 root N naught hertz. What we are using in the previous session as well as this session in the plasma frequency numericals, this is what we do. Fine. And another thing is there, which is the plasma parameter, which is, I am writing here, plasma parameter, which is important also, that is number of electrons present in a unit sphere of influence, that is radius is lambda d, and this is given as lambda as 4/3 pi lambda d cube into n. That's all. Now quickly we do 4 numericals, which are simple numericals, so we can then wrap up with this. Just a minute. Yes. Given if the electron density of the ionospheric layer is this, therefore n of E is 2 into 10 to the power 11 per meter cube. No need to change units, it is given. What is the plasma frequency at 850 degrees Celsius? Plasma frequency, as you can see, does not depend on temperature. So just apply F is equal to 9 root n naught. So just apply that, root 2 into 10 to the power 11. It's a simple. This is for confusing thing, not required. Isn't it? Now, if we take the root of this, it's about this into 9, approximately about some 40 megahertz kind of coming, but I have to check it again. Just a minute. No, 4 megahertz, sorry. It's about 4.02 megahertz. Okay, so this is the simple solution we have done in this assignment also, so this will be helpful. For the previous question, what will be the number of particles in the Debye sphere? See this, oh sorry, just a minute. Yeah, this thing, this number of particles in the Debye sphere is nothing but the lambda parameter or plasma parameter. Now for this, what we require, if you write the formula, it is 4/3 pi lambda d cube into n naught or ne whatever. But n naught is known because in the previous question we know, but we don't know this lambda d. We know the formula of lambda d. So what is the formula of lambda d? It is root over epsilon naught kb into T. Now this temperature will be used, which is given in the previous, so n naught into E square. So temperature was how much? 850 degrees Celsius. So it will be have to be converted into Kelvin. 850 plus 273 comes out to be 1123, I think. Yes, 1123 Kelvin. What is the value of Kb? It's 1.38 into 10 to the power minus 23 joules per Kelvin. And what is epsilon naught? Again I am writing the value 8.85 into 10 to the power minus 12 Newton per kg square per Coulomb square. Sorry, Coulomb square will be in the multiplication, and I have written here also wrong. No, Newton meter square per Coulomb square. This is fine. I have written here wrong. I am writing gravitation. Newton meter square per Coulomb square. Yeah. Okay. And what is E? 1.6 into 10 to the power 70. Okay. So lambda d can be easily found out. So if you put all these parameter, just I am putting it 10 to the power minus 12 into 1.38 into 10 to the power minus 23, sorry, into 1123 divided by 2.11 into 10 to the power 11, sorry, 2, it's 2 into 10 to the power 11 into 1.6 into 10 to the power 19 minus 19 whole square. Now if you do it, all the calculation which I have calculated so far, so it is 5.17, it's 10 to the power minus 3. Now we know this, now we can calculate easily. So it's 4/3 into 3.1416 into 5.17 into 10 to the power minus 3 whole cube into 2 into 10 to the power 11. Now if you calculate it, how much it comes out, you can check it just into 3.1416 into 2 into 5.17 into 10 to the power minus 3 cube into 10 to the power 11. So about 115768 is the lambda. Okay, next question is, given the electron density of plasma to be this, what is the debye length? So we can easily calculate now. Given n naught is 10 to the power 20, I have given some arbitrary value. In the ionosphere this is not possible, I think 10 to the power 20, because if one layer we know that maximum is 10 to the power 12. Okay, so length of temperature, this temperature is 1300 Kelvin. We need to find out debye length. Again, just write the formula, epsilon naught kb T divided by n naught E square. Just write it. So it will be 8.85 into 10 to the power minus 12 into 1.38 into 10 to the power minus 23 into 1300 Kelvin divided by 10 to the power 20 into 1.6 into 10 to the power minus 19 whole square. Now if we calculate it, let's see, 8.85 into 10 to the power minus 12 into 1.38 into 10 to the power minus 23 into 1300 divided by 10 to the power 20 divided by 1.6 into 10 to the power minus 19 whole square. The root of answer is very small because I have taken this as too much, 2.49 into 10 to the power minus 7 meters. Okay, this is the answer. Okay, the last question here is, at 1200 Kelvin the plasma frequency is 2 megahertz. Calculate the debye length. Well, temperature is given. What more is required to calculate debye length? See, for calculating debye length, we need n naught and temperature, because other things are known. Now it is better to calculate all those other parameters which are constant. That will be helpful. So n naught is not given, so I will take it from this. Therefore omega plasma is 9 root n naught, right? Now this is given to be 2 megahertz, that is 2 into 10 to the power 6 hertz, 9 root n naught. So it will be, square it, so it will be 4 into 10 to the power 12 divided by 81. that is N naught. Just check it. Yeah, it comes out to be 4.93 into 10 to the power 10 per meter cube. This is N naught, right? Fine. Now you just calculate lambda d again with the same formulation. I am not writing the formula, just writing this. 10 to the power minus 12 into 1.38, the Boltzmann constant, 23, and 1200 Kelvin is given, no need to convert further. And this is 4.93 into 10 to the power 10 into 1.6 into 10 to the power minus 19 whole square. Let's calculate how much it comes. 8.85 into 10 to the power minus 12 into 1.38 into 10 to the power minus 23 into 1200 divided by 4.93 is divided by 10 to the power 10 divided by 1.6 into 10 to the power minus 19 whole square. This is what we have get, and an answer it's about 0.0107. So this is the dividing. Another thing is the mean collision time kind of thing which is there in the plasma. So I was just want to tell some formulation. Just remember this. Some extra may be helpful in solving the assignment. So this nu EI is the electron ion collision rate, or you can say the mean collision rate. Okay. So this nu EI divided by the omega plasma is actually given as Z. This is the atomic number, log of lambda divided by 10 nd. Okay. Now this log of lambda, this is not the device parameter. Yes. So this log of lambda. Okay. So this is not device parameter. So log of lambda is roughly 9 nd by Z. Z is the atomic number. So if we put, we get by omega plasma is actually 9 by 10. So this is a important relation which may be helpful in solving certain questions in the assignment. Fine. Now it's almost done. Just a minute. Just check the formulation once again. Okay, so we can discuss in the next class also. But this is the expression which you can see of. So 1 by nu is nothing but the collision rate time. So we can easily solve certain questions. So all these numericals will be helpful in understanding purposes and solving the assignments. So I will end up here. Okay. Okay. So I stop the screen. Goodbye.